So. Okay. So. Okay, also, ich zeichne es jetzt selbst auf und ich hoffe, dass ihr mich auch hören könnt. Ne? Also, gut, sehr gut. Ich hoffe, ich mache es nicht umsonst. Also ich versuche es, dass es klappt. Es sollte eigentlich gehen. Und ihr könnt ja gebt mir noch mal kurz Daumen hoch, wenn ihr den ANSYS-Bildschirm seht. Wenn ihr alle den Bildschirm seht. Ich sehe ihn jetzt nicht, aber ich hoffe, ihr seht ihn. Okay, also, dann wechsle ich jetzt mal zu Englisch und mache die Beschreibung in Englisch. Und ich habe euch hier auch schon das Modell aufgebaut. Wir bauen das jetzt aber nochmal zusammen nach. Okay, ladies and gentlemen, we start the airfoil optimization. First, I create a new project and I call it, let's call it airfoil design number 2. So, call it airfoil design optimization. Okay. And as a first step, before we use our design exploration tools here at the bottom of our workbench, we must create a simple CFX model for the airfoil. So I track the fluid flow problem onto the workbench, and first step, as the same as last time, we have to create a geometry. So I go to right click, I start the design modeler geometry. Okay, and it takes some time. Okay, I have to share the full desktop. You can see it. Okay, and now give me thumb up if you can see the workbench design modeler. Give me short thumb up. Okay, perfect. So I choose my plane. I choose the XY plane with the red and green arrows and set to the top. Okay, and I scroll a bit inside. So I want to make a wing. It should be about 1 meter. So I have to scroll in a bit. And then I create my first wing. I go to splines and I want to create it with, let's say, let's maybe try 3 different splines. We make it a bit more easy. You can make it more complicated later. I do a left mouse click, and again a left mouse click, and I go to open end, and I have created my first spline, and now it looks a bit edgy. That's not really good. I want to cut, I cut it again, and I zoom out a bit. Okay, and again I draw a spline, and probably won't be so edgy now. I close it with open end. Okay, that's the nose of my wing. And now I make the wing a bit more easy. I just want to use 3 splines. I do a left mouse click on the bunch in the middle and a right mouse click here, and I take the last spline. I do it like this. Open end. Okay, that's a nice wing. It looks pretty good. And I can go to extrude, and I take the same settings as last week, and I think it was 10 meters wing. Of course, that's a quantity I should not change. Yeah? The 10 meters should always be fixed. This should not be an optimization parameter. I go back to the sketch and I hide the extrude so I can work a bit better. And now I want to define my optimization parameters. To do it, I need construction points. I want to set 1 point here, 1 point here, and let's say 1 point here. Okay. And now now I can do a CFD simulation. My construction is finished, but I want to do later an automatization of this construction. So I want to design a lot of different designs without doing anything. The computer should find the design points for me. So I have to define some dimensions. So I go to dimensions. I click to horizontal. And now I can click again on this bunch, and I can define here a horizontal dimension. And you see here, now we have taken a dimension, and the dimension is also listed here on the side. So I can change it by hand, and I can use really defined values. For example, 0.3. And additionally, I want to do a vertical dimension. Go from here to here and find a vertical dimension. Let's take 0.25. Yeah? Go back to generate. And now I can have defined parameters. So if I now go back to the parameters and change it to 4, my dimension will be changed automatically. Or if I go here to 1, it will be flatter. Yeah? But now what you see, the flatness is not really convenient here. It doesn't look really nice at this. If I take this parameter, so maybe 0.15 was a change that was too big, too much, and I have to define a range. Yeah? And it gets fatter. Okay, and what I now have to do, I have to document which parameter I change. Yeah? To document it, I start a PowerPoint presentation to copy, and maybe you can go to your old slides and start a new presentation here. And you should document it well, because it will be a bit complicated now. You will have a lot of different changes now. So I go to my documentation, I make a screenshot, and I copy it here onto my PowerPoint presentation, and I crop it a bit. Okay. Let's say this is my first parameter. And now I want to define some more parameters. I can, for example, I take this bunch here at the bottom. I define it again, horizontal, this, and vertical like this. Okay, and I take these values. Okay. This, so it's we have better values. And what else can we take? I think we have two parameters now. Maybe we change the nose a bit. Can also take here horizontal, change it to okay, not so good. We need it vertical. Change this. Okay, then we can change the nose a bit. Yeah, can stretch the nose a bit. Okay, that looks pretty cool. I think that's enough now. Later you can take more parameters if you like, but at the beginning we just will concentrate on this 6 parameters. I think that's fine for the beginning. So again, I make a screenshot for my documentation. Okay. I document it, I crop it a bit. You can see the PowerPoint, huh? Give me a short thumb up if you can see the PowerPoint, or if it is hidden. Okay, so and then I have my coordinate system, so I can see it. Okay, and so now we have a parameterized geometry. Yeah, we can just change the numbers here in this table to get a new geometry. And we can unsuppress also the our geometry, and we can design our wing. Okay. And what else do we need? We need we now have to define the boundaries. So we define it as airfoil. So I press Control, I use a mouse to select the whole geometry, and then I press the right mouse button, I create a new named selection, I go to Supply, Generate, and then I have created my new named selection. And now you have to rename this named selection to airfoil. Or you can call it wing, or you can call it any other name, but you have to give a special name. Okay, and like in the other exercise now, like you already know it, we need now an enclosure. I want to create it. You go to Tools, Enclosure. You choose a cylindrical enclosure, a cylinder, and the axis should be the x-axis. And the surrounding should be about 10 meters. Then you can create it. And that's not so good. I have to delete it again. I want to create it in another direction. So I do it again. I go to Enclosure. I choose a cylinder here. I have to define the direction, and it is set direction, and the cushion is already set to 10 meters. And so, okay, but that's a bit too big. 1 meter. Okay, that's pretty fine. It looks good. Now we have our surrounding, and again we have to define where the air should flow, where it should enter our dimension. So we go to left mouse click and we define the named selection. I press apply, go to generate, go to named selection, rename it, and I call it opening. So now, up to now, it's totally the same as in our last exercise, but the only difference is that we define some dimension. So now Mr. König, you like to take the control. Okay, it was a mistake. I regret it. And okay, I go again to generate, and everything is fine. So now I have to go back to the sketch 1. And if you look closely to the dimensions, we have defined 6 dimensions. And what I do now, look closely, I press to here at the beginning, this small box. I select it, and this is a feature to define parameters outside the workbench. So if I press it, I can use these dimensions also outside in the workbench, and I can copy all these dimensions to other programs. Okay, and now I close the design modeler, and what you see now, before I do anything, I save my workflow, and now you see here a set of parameters was added, a parameter set. And if I now double click on parameter set, I can see all these parameters here in a spreadsheet, and now I can change it here in the spreadsheet. For example, I can change this to another value, and then I can use other values, for example. And this is really cool feature to make optimization, and if you want to make a lot of calculations, then it's now really easy to change all the values. Okay, before I go on, I want to create the mesh. And of course, the mesh will be done more or less automatically. It will be a tetrahedral mesh, and it will take some while. And the mesh have to be created. Normally, you can also define mesh parameters as a parameter set. For example, if you want to make finer or coarser meshes automatically, you can define this in the Workbench. Yeah, you can make an additional parameter set. We don't want to use this feature now because we do not need it, but you can if you want. Okay, let's go on to setup. I go to edit. Okay, it takes some time. So here you see the domain, and one step is now important, and I want to mention it again because there was some trouble to some of you. If you have now two meshes, you have a mesh inside the wing and you have a mesh outside the wing. And we only want to calculate the mesh outside the wing. So we don't want to use the B15, we only want to use the B43. And please be careful, the names can be different in your models. These are the meshes that are here. We have a mesh of the wing and a mesh of the air, and we only want to make calculations in the air surrounding. So you have to go to default domain, and now you have to choose only the domain 43. This is an important step. And if I now go to OK, he will not use the domain outside. Okay? So, and we have to define our boundary conditions. We call it again airfoil. This is a surface of our wing. It should be a wall, and we choose all the boundaries we need here. And you choose all except the surrounding areas. And this is now the wall of our wing. It is really important that you take all the areas, because if you do not define all the areas, your force calculation later will be wrong. Yeah. So always control it a bit. Scroll with the mouse inside to check if you have defined everything. Okay, then I go to OK. And again, I enter it again to show you something. Here's a feature, smooth wall. Later, we can also choose rough walls. Yes, yes, Mr. Walsh has written in the chat, yeah, you can rename it afterwards. Of course, that's also possible. Then it's more easy. You just don't have to mix it up. Yeah? Be a bit careful. Okay. So now this airfoil is defined. Now we have to define the opening. And the opening, we can take all the other boundaries. We can rename it opening. And we have to define it as an opening. Yeah, we have to define the velocity. In our case, it's velocity in x direction. And we want to take the same velocities as last week. We'll take the 600, 0, and 0, and we go to apply, and then we have to define our two boundary conditions. One thing you have to check, please always check if we have air, so we don't want to, Mr. Schmidt, perfect. I made a small mistake. Of course, we want to take kilometers per hour. 60 meters per second is much too fast. It is better to take 600 kilometers and go to apply. Okay, now we're finished, but we're not totally finished. I want to define an expression. So okay, I insert an expression and I name it total force, or let's call it total efficiency. Total efficiency force. And now I want to create an expression. In an expression you can calculate any values, or you can calculate, for example, forces at special locations. And I want to take to define it at them. Okay. Just want to check something. Force Y divided by X. Okay. This should be our total efficiency. And I also want to add another expression. Lift force is force epsilon at F1 apply, and I can also duplicate this and edit it again. And change this to force X. Okay. This should be enough. Force does not exist. Let's try it like this. Maybe it's a wrong definition. ANSYS. Let's try it like this. Okay, we try it like this. We will see later if this was right. If it's not right, we can evaluate some other. We can evaluate it also in post. Okay, never mind. We try it. Okay, we go to outline. And now I also want to use this force as a workbench. We will use it later in post again. Maybe I delete it. I delete it. We try this later. We keep it simple at the beginning. So just close it. And everything was all right. So we do our first simulation. I go to update and I have a look in the yeah, it's better. Don't use this expression feature at the beginning. Try it first without any expressions. The expressions could be a little bit dangerous because you can define it and there will be no error message, but later in the workflow you will get a problem because something from the syntax is not right, and then you have difficulties in finding the problems. Okay. This is if you have a look now at the convergence, this is a bit crazy now. We see the convergence is going up again. Yeah, this is a bit strange. Maybe we have to change something. But now it goes down again. Yeah, I think this behavior, this solution of the Navier-Stokes equation is something new. Yeah, you see, first the numerical simulation converges, then it rises up again, and, and then it converges again. But I can tell you why this effect happens. It's probably because we have defined the walls at the sides also as surroundings, and this will have some turbulence-like effects that causes rise here in the convergence. But it's not a problem. The solution is here. Maybe it's a bit more difficult for the solver to get a solution, but we will have a look if everything is right. And now we go to post and have a look at our results. Okay, let's insert some streamlines and everything looks fine. Can have a look at the pressure. It changed. I always switch from scientific to fixed. and it looks good. Here it looks fine. We have some high cracks at the nose. We have high pressures here. That's normal because of the drag. We have a blue area here at the top of our wing. We have a low pressure and a higher pressure at the bottom. And this is good optimal. This is quite not so bad, this design. And I want to have some string traces, and they're pretty fine. I think that's okay. So now I want to evaluate the forces, and maybe if you are now online, I want to show you also the plane feature. You can look at some pressures, yeah. That's a good view. Makes sense, yeah. You can see at the top we have a low pressure region, and the front we have a high pressure region. So we have even a low pressure field underneath the airfoil. This will cause forces into y direction. This is how it should look like. Now I want to evaluate the forces, and I want to have a look at the forces in y direction. Calculate. Okay. And in x direction. Okay. Looks good. Now I try to create my expressions here. Lift force. Okay. Okay. Force X. So sometimes he didn't like my syntax, but I think that's fine. Now he has defined it. And I want the drag force. Airfoil. Okay. And you can make also a short evaluation to see if everything is all right. Okay. It makes sense. ANSYS can calculate everything. Yeah. And now I want to define my new efficiency for the forces. So the new parameter should be let's call it efficiency for airfoil. That's a good name. You have to take care a bit that you don't use names that are already used inside this expression. Yeah, if you use it twice, it can cause a problem. And I want to take lift force over drag force. Drag force. And if everything is okay, if he can find your values here, he will write it in Courier typing. So And now I want to define these parameters also as output Workbench parameters. Don't use input, use output Workbench parameters. So that's okay. I close it. Don't forget to save the workflow. And now you see here is a parameter set that is used as input parameters, and there is a parameter set used as output parameters. So you have defined both. And you can now double click on this parameter and you see your inputs for the geometry and your outputs for the geometry. And you have your efficiency, it's 10.874 for the efficiency of your airfoil. And now you already know this value maybe from your from your homework. And now what we can do now, we can now add an automatic optimization. So our automatic optimizer will now find parameters that have the best efficiency for your airfoil. And this is done by a design of experiments study. And I think that's a really powerful tool. That's something you will need more often. Okay, I want to have a short look at the exercise to do it totally in the same way. Okay, get the response surface optimization. So you edit here, and there are a lot of different methods for this. There are a lot of different mathematical methods to do it. Like neural networks, and it is an artificial intelligence. Maybe you've heard about KI or AI. It's künstliche Intelligenz, artificial intelligence. Now there is an artificial intelligence model in this new version of ANSYS, and you can use it to find optimal geometries. And there are different methods, neural networks or generic algorithms or swarm optimizations or particle swarm optimizations or Latin hypercubes that can be used for this optimization. And later on you can also change the method if you want to use another. Okay, so here are now our parameters we want to change. You have to enable them by a tick, and these are our goals. Are our goals we want to optimize. And now we go to update, and now ANSYS will create a lot of points. Okay. And if you now have a look here in the table, you can see all the simulations that have to be done now. Yeah, he has to do 44 different simulations to find the optimum geometry. And that's now a point that will take a long time. Yeah, you will need some hours or overnight And I think now, before we do this, the first simulation is finished, but you can imagine it will take some time now to do all the simulations. Look here, now he starts all the calculations, and we can't wait so long. So I want to open an old case that I have already prepared for you. Okay, so I want to stop it. And hopefully he will not start the next case immediately. Okay. So you have to do a lot of calculations in the back. Okay. I want to open the next. Now he tries to. Okay. I will close it. Now that's now a bit difficult to stop it if it wants run. Okay, I go to my old test case. Okay, save this one. And I will open the test case I have already prepared for you. And now I'm in this old test case, and I want to have a look at all the designs. Here are all the designs. I made a lot of calculations for you. It was about 80 in this last step. Here you can choose the optimization method. I will come to this a bit later. And you can go to this response surface tool. And here in this response surface tool, you now can change the parameters. You can, here are all the results. All the results are saved now. And you can have here these points that are different CFD simulations. So I did 80 CFD simulations for this run. I changed 80 different parameters for all the runs. And now I can find an optimal solution. For example, if I have here the X force, and I change one parameter in this direction, I can have a higher X force too here. And I can also show you the Y force. These are the Y force. And here you see it pretty cool. It is not a linear behavior for this parameters. Here you can get a real local minimum in this simulation. So you can find some optimum solutions. And you can change all the parameters now if you like. Change it like this. get to examine your results a bit. Okay. And maybe one last question. What is a what is a high force? If you want to find a geometry with a high force parameter, you have to go into this direction. And if you want to get a wing with a low force, you have to choose this design. Or if you want to have a design with a high y force velocity, you choose this design. Okay. You can find it here by this plots. Or you can also refer to the whole table, yeah. And another plot I want to introduce to you is this so-called sensitivity analysis. This will show you how big is the influence of a parameter to the force. For example, the biggest influence has this parameter h1, and a small influence has a parameter v2, and a bigger influence has a parameter h7. But I think this h1 is one of the has more or less the biggest influence. Yeah. Okay, I think that's maybe you can have a look at the designs. You can now also, if you want, you can also copy this table to Excel, and you can find the point with the lowest drag force and the highest lift force, and that's your optimum design. Yeah. And I think you can even do it in the Workbench. That's something I never tried, but I think you can create an Excel sheet from this lot. No. Okay. Oh, that's not so easy. Can copy it. Okay, that's cool. Now we can plot this variable over this. We can always take a dot, some dots, yeah. Some scatter plots, dots, and okay. I think you know what I mean. Now you can take the design with the highest forces, the lowest drag force, and the highest lift force. Okay, And I think that's a job you can do on your own. I think I have explained everything. Maybe we can stop the video now. And if you have further questions, we can ask, we can explain them afterwards. Huh? So, Mrs. who started the video, Mrs. Keller. Or stop, I started it. Sorry. Stop it. Okay.